Hello there, and welcome to Beyond the Cosmos, where the biggest questions in science are explored at the pace of a slow breath, where curiosity is never rushed, and where the universe unfolds one careful thought at a time. Tonight, we are going to travel towards something that, when you first hear about it, seems to break one of the most fundamental expectations we carry about the cosmos. We tend to think of space as cold, certainly, the silent vacuum between the stars chilling anything exposed to it down toward the lowest temperatures physics allows. But there is a particular place, a real, identifiable, measured place, roughly 5,000 light-years from Earth, that is colder than the space around it. Colder, in fact, than the universe itself has any obvious right to allow. We are going to call this place, tonight, the coldest place in the universe. Its name is the Boomerang Nebula, and the story of why it is so cold, and why that coldness is so strange, is one of the more delightful puzzles that modern astrophysics has had to solve. It will take us through the physics of dying stars, through the strange behavior of gas expanding into a vacuum, through the absolute limits that thermodynamics places on how cold anything can ever become, and through the patient detective work that eventually explained how a small, unassuming patch of gas in the constellation Centaurus came to hold a record that by all the ordinary rules of the universe it should not have been able to hold. Before we set off, I want to ask where you are tonight. Perhaps you are curled beneath blankets, the warmth gathering slowly around you as the room cools. Perhaps you are in a chair with the heating murmuring somewhere nearby, the day's last light fading from the window. Wherever you are almost certainly warmer right now than the coldest spot we will visit tonight. Warmer by a margin so large that the comparison itself becomes part of the wonder. Tonight, we will travel toward true cold, the kind that approaches the absolute floor of temperature itself, and see what the universe had to do to get there. If this kind of slow, careful exploration of the universe helps your mind settle into rest, it would mean a great deal if you tapped the like button or subscribed to Beyond the Cosmos. It helps more people who are looking for a calm voice to think alongside find their way here too. Now, let your body sink a little further into wherever you are resting. Take one slow breath in and let it go without hurry, and let's begin. To understand why the Boomerang Nebula's temperature is so startling, we first need to spend some time with the concept of cold itself, because cold, in physics, is a far more interesting and far more carefully bounded idea than it might seem in ordinary life. In everyday experience, we think of temperature as a simple scale running from cold to hot, with no particular limit in either direction. A winter morning is cold. A blast furnace is hot. We rarely think about whether there is some ultimate floor beneath which temperature cannot fall. The way there obviously is no ultimate ceiling above which temperature cannot rise, since stars and supernovae and the early universe itself demonstrate that temperatures can climb to staggering heights. But cold is different. Temperature, at its most fundamental level, is a measure of the random motion of particles, the jostling and vibrating and colliding of atoms and molecules that make up any substance. A hot object has particles moving rapidly, colliding frequently, vibrating with large amplitude. A cold object has particles moving more sluggishly, with less energy to spare for motion. As you remove energy from a substance, cooling it further and further, the particles within it slow down more and more. There is a natural endpoint to this process, a temperature at which particle motion would, in principle, cease almost entirely, reduced to the smallest residual vibration that quantum mechanics allows even in principle. This temperature is called absolute zero, and it sits at 0 on the Kelvin scale, equivalent to about minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit. It represents not an arbitrary number on a human-invented scale, but a genuine physical floor, the coldest that anything can theoretically become. The key word here is theoretically, because absolute zero is not just difficult to reach. It is, according to the laws of thermodynamics as we currently understand them, impossible to reach exactly, no matter how sophisticated the technology or how much energy and effort is invested in the attempt. The third law of thermodynamics establishes that as a system approaches absolute zero, the amount of additional cooling achievable for any given amount of effort grows smaller and smaller, asymptotically approaching but never quite touching the absolute floor. Scientists in laboratories on Earth have managed to cool small samples of matter to within a tiny fraction of a degree above absolute zero, astonishingly close. But the exact value of zero, Kelvin itself, remains, as far as we understand the physics, permanently out of reach. This matters enormously for what we are about to explore tonight, because the question of how cold something in the universe can naturally become is not just a question about engineering or effort. It is a question about the deepest structure of physical law. And the Boomerang Nebula, as we will see, comes remarkably close to that ultimate flaw. Not through any deliberate engineering, but through a natural process that nobody, before it was discovered, expected the universe to be capable of producing on its own. Before we travel to the Boomerang Nebula itself, it helps to establish a baseline, a sense of how cold the ordinary, undisturbed vacuum of deep space actually is, so that we can appreciate just how unusual it is for anything to be colder than that baseline. Space, far from any star, far from any galaxy, far from any source of light and warmth, is not a perfect vacuum at absolute zero. It is bathed everywhere, in every direction, by the faint glow of the cosmic microwave background, the ancient afterglow of the Big Bang itself. This radiation, the oldest light in the universe, was released roughly 380,000 years after the universe began, when the cosmos had cooled enough for atoms to form and for photons to travel freely without being constantly scattered by free electrons. Since that moment, nearly 13.8 billion years ago, this radiation has continued to travel through an expanding universe, stretching and cooling along with the space it moves through. Today, the cosmic microwave background has a temperature of approximately 2.7 Kelvin, just under 3 degrees above absolute zero. This is the natural, universal floor of temperature that anything sitting in deep space, isolated from any other source of heat, will eventually settle toward, because the microwave background radiation is everywhere, filling every corner of the observable universe, and any object floating in deep space will continuously absorb a tiny trickle of energy from this ancient glow, just as it radiates its own energy away into the surrounding emptiness. This 2.7 Kelvin baseline is itself an almost unfathomably cold temperature by the standards of ordinary human experience. It is colder than anything found naturally on the surface of the Earth, colder than the coldest recorded temperature in Antarctica, colder than liquid nitrogen, colder than nearly every substance encountered in daily life. And yet, for most of the history of astronomy, this 2.7 Kelvin background was assumed to represent something like the practical floor for naturally occurring temperatures in the universe. Objects in space could be heated well above this temperature by nearby stars, by their own internal processes, by friction, by countless other mechanisms. But cooling below this universal background radiation seemed, for a long time, like it should be essentially impossible, because the background radiation itself was constantly supplying a small but steady trickle of warmth to anything sitting in its path. This is precisely the expectation that the Boomerang Nebula overturns. When astronomers first measured its temperature in detail, they found something colder, significantly colder, than the 2.7 Kelvin background that should, by all reasonable expectation, have represented the practical floor. Understanding how this is possible requires us to set aside the simple picture of space as a passive, uniformly cold backdrop, and instead think carefully about what happens when matter itself is actively, violently expanding outward into that backdrop at extraordinary speed. The story of the Boomerang Nebula begins, as so many cosmic stories do, with the death of a star. Not a violent, explosive death of the kind that produces a supernova, but a slower, more gradual kind of ending, the kind experienced by stars of roughly the same mass as our own sun. Or perhaps somewhat more massive as they exhaust the hydrogen fuel in their cores and begin the long, complicated process of transitioning from a stable, middle-aged star into something else entirely. When a star like the Sun begins to run low on hydrogen fuel in its core, the core itself starts to contract under its own gravity, while the outer layers of the star, no longer held in check by the outward pressure of core fusion in quite the same way, begin to expand dramatically. The star swells into what astronomers call a red giant, growing to many times its original size, its outer atmosphere becoming progressively more loosely bound to the star's gravity as it puffs outward. During this red giant phase, and during the subsequent, even more extended phase known as the asymptotic giant branch, stars become remarkably effective at shedding their outer layers into space. Strong stellar winds, driven by a combination of radiation pressure and the star's own pulsations, carry vast quantities of gas away from the star's surface, gradually stripping the star of much of its original mass and scattering that material outward into the surrounding interstellar environment. This process of mass loss, repeated and intensified over thousands of years as the star approaches the very end of its life, is responsible for producing what astronomers call a planetary nebula, a glowing shell of expanding gas surrounding the small, hot, exposed core of the original star, which has, by this point, shed its outer layers entirely and is on its way to becoming a white dwarf. The name planetary nebula is something of a historical accident, dating back to early observers who, looking through primitive telescopes, thought these glowing shells resembled the disk of a planet. They have nothing to do with actual planets, but the name has stuck for centuries. The Boomerang Nebula is one such object, a star in the late stages of its life, caught in the act of shedding its outer layers into the surrounding void. But what sets the Boomerang Nebula apart from the many other planetary nebulae that astronomers have catalogued over the decades is the sheer ferocity and the sheer speed of the mass loss occurring there. A process so intense, so much more vigorous than the gentle, gradual mass loss of an ordinary dying star, that it has produced, as a direct physical consequence, one of the strangest and coldest environments known anywhere in the observable universe. To understand why rapid mass loss leads to extreme cold, we need to think carefully about the physics of gas expanding into a vacuum, a phenomenon that is actually familiar in a much smaller, much more everyday context, and that becomes genuinely extraordinary when scaled up to the size of an entire dying star's outer envelope. When a gas is compressed into a small volume and then allowed to expand rapidly into a larger volume, it cools. This is the same basic principle that makes an aerosol can feel cold to the touch after you spray it. Or that explains why the gas escaping from a compressed cylinder, like the carbon dioxide cartridge used to inflate a bicycle tire, comes out noticeably chilled. As the gas expands, the molecules within it do work, pushing against their surroundings, expending energy in the process, and that expenditure of energy translates directly into a drop in temperature, because temperature, as we discussed earlier, is fundamentally a measure of the energy contained in the random motion of those molecules. This process, known to physicists as adiabatic cooling, or more specifically in this astronomical context, as the kind of cooling associated with rapid, large-scale expansion, becomes dramatically more powerful as the rate and the scale of the expansion increase. A small puff of gas escaping a tiny nozzle cools by a modest amount. But the outer envelope of a dying star, shedding an enormous quantity of mass at extraordinary velocity into the vacuum of space, undergoes an expansion on a scale that dwarfs anything achievable in a laboratory or an everyday household object. The Boomerang Nebula's central star is losing mass at an estimated rate of roughly 1/10,000th of the Sun's mass per year, a staggering rate of mass loss compared to typical planetary nebulae, where the central star usually sheds material far more gradually. This gas is being ejected outward at speeds of around 164 kilometers per second, dramatically faster than the gentle outflows of roughly 10 to 20 kilometers per second typically seen in more ordinary planetary nebulae. This combination, an enormous quantity of gas ejected at extraordinarily high speed, expanding rapidly into the surrounding vacuum, produces an adiabatic cooling effect of remarkable power. The gas, as it rushes outward and expands into an ever larger volume, loses energy to that expansion at a rate intense enough to drive its temperature down well below the 2.7 Kelvin floor that the cosmic microwave background would otherwise impose. This is the fundamental mechanism behind the Boomerang Nebula's extraordinary cold. Not some exotic unknown physics, but the same basic principle of expansion cooling that makes an aerosol can feel cold in your hand, scaled up to a process involving a mass of gas many times larger than the entire planet Earth, rushing outward at hundreds of kilometers per second into the emptiness of interstellar space. The actual measured temperature of the Boomerang Nebula, when astronomers first determined it in detail in the mid-1990s, came in at approximately 1 Kelvin, just 1 degree above absolute zero. This is significantly colder than the 2.7 Kelvin cosmic microwave background, making the Boomerang Nebula, at the time of its discovery and for a considerable period afterward, the coldest known natural object anywhere in the observable universe, colder even than the ambient temperature of the universe itself. It is worth pausing here and letting the strangeness of that fact settle in properly. Every other natural environment we know of in the universe is, in some sense, warmer than its surroundings, or, at the very coldest, equal to the ambient background temperature provided by the cosmic microwave background. Deep, empty intergalactic space, far from any star or galaxy, settles toward that 2.7 Kelvin floor and stays there because there is no mechanism present to push it any colder. The Boomerang Nebula, by contrast, has found a way to actively, dynamically cool itself below that universal floor, not by isolating itself from the microwave background's gentle warming influence, but by counteracting that influence with an even more powerful, ongoing cooling process driven by the sheer violence of its own expansion. This makes the Boomerang Nebula's temperature, in a very real sense, a temporary, actively maintained state rather than a simple, passive equilibrium. The gas within the nebula is not cold because it has been left alone for a long time to settle towards some natural resting temperature. It is cold because it is, right now, in the present moment that we observe it, in the midst of an extraordinarily energetic expansion that is actively driving its temperature down faster than the cosmic microwave background can warm it back up. This is a crucial distinction, and it is part of what makes the discovery and the explanation of the Boomerang Nebula's temperature such an interesting scientific story, one that required astronomers to think carefully not just about what temperature the nebula had, but about the specific, ongoing physical process responsible for maintaining that temperature against the gentle, constant warming pressure of the universe's background radiation. The history of how astronomers actually discovered and measured this extraordinary cold is worth exploring in some detail, because, much like the story of the Great Attractor that we explored in a previous episode, it is a story about indirect detection, about inferring something remarkable from careful, patient measurement rather than simply observing it directly with the naked eye or even with an ordinary optical telescope. The Boomerang Nebula itself had been known and catalogued for some time before its extreme temperature was understood. It was first observed and described in the 1980s, and it earned its name from its appearance in early ground-based optical images, which showed two faint, symmetric lobes of glowing gas extending outward from a central point, vaguely resembling the curved shape of a boomerang. This visual appearance, while evocative, gave no particular hint of the extraordinary thermal properties hiding within the object. A boomerang shape is, after all, just a shape, and there was nothing in the visible light images alone to suggest that the gas comprising that shape was colder than anywhere else in the known universe. The breakthrough came when astronomers turned radio telescopes toward the nebula, specifically instruments capable of detecting the faint microwave and millimeter wavelength radiation emitted by carbon monoxide molecules within the expanding gas. Carbon monoxide is a particularly useful molecule for this kind of measurement because it emits and absorbs radiation at very specific, well-understood wavelengths, depending sensitively on its temperature and the surrounding physical conditions. By carefully measuring the way the nebula's gas absorbed the background radiation of the cosmic microwave background itself, observing the gas essentially silhouetted against the ancient glow of the Big Bang, astronomers in 1995 were able to determine, with considerable confidence, that the gas in the outer regions of the Boomerang Nebula had a temperature of approximately 1 Kelvin. This measurement technique, observing how foreground gas absorbs the background microwave radiation passing through it, is itself a beautiful piece of astronomical ingenuity. It does not require the gas to be glowing brightly enough to detect directly. Instead, it uses the universe's own ancient background light as a kind of cosmic backlight, with the cold gas of the nebula appearing as a subtle dip, a slight absorption against that otherwise uniform background glow. The precise wavelength and depth of this absorption feature allowed astronomers to calculate the gas's temperature with considerable precision, revealing a result that immediately stood out as remarkable. A temperature colder than the background radiation being used to measure it in the first place. When this result was published, it generated considerable interest and some initial scrutiny within the astronomical community, precisely because it seemed to challenge the everyday intuition that nothing in the universe under normal, natural circumstances should be able to sit colder than the universal background radiation bath that permeates all of space. Follow-up observations using different instruments and different techniques confirmed the basic finding, and over the following years, the explanation we have already discussed, the extraordinarily rapid and extraordinarily massive outflow of gas from the dying central star, driving powerful adiabatic cooling, became the well-established and widely accepted account of how this remarkable temperature was being produced and sustained. Let's spend some time now with the central star itself, the source of all this dramatic activity, because understanding what kind of star can produce an outflow this powerful tells us something important about just how unusual and short-lived the Boomerang Nebula's extreme cold actually is on cosmic timescales. The central star of the Boomerang Nebula is generally understood to be a star transitioning rapidly from the asymptotic giant branch phase we discussed earlier toward becoming a planetary nebula proper, caught in an unusually intense and unusually brief period of unusually vigorous mass loss. Stars passing through this phase of their lives typically do so over a period of mere thousands of years, an astronomically brief interval compared to the billions of years such stars spend in earlier, more stable phases of their existence. The Boomerang Nebula appears to represent an even more extreme and even more compressed version of this already brief transitional phase, sometimes described by researchers as belonging to a category of objects experiencing what is called a superwind, an episode of mass loss so intense and so much faster than typical planetary nebula formation that it likely lasts for a comparatively short window, possibly only a few hundred to a couple thousand years, before the rate of outflow naturally diminishes as the star's outer envelope becomes progressively depleted of material to expel. This temporal brevity is an important part of the story because it means that the extraordinary cold we have been discussing tonight is not a permanent, settled feature of this particular star system, but rather a fleeting dramatic episode, a kind of astronomical fireworks display playing out over a timescale that, while still vastly longer than a human lifetime, is remarkably short by the standards of stellar evolution more broadly. The Boomerang Nebula, in other words, caught our instruments at a particular special moment, a brief window during which the underlying physics of stellar death happened to produce conditions extreme enough to set a record for natural cold anywhere in the known universe. This raises an interesting question that we will return to later in our exploration tonight. How many other objects throughout the universe might be passing through similarly brief, similarly extreme episodes of rapid mass loss at any given moment? Episodes that might, in principle, produce comparably extreme cold, but that we simply have not yet observed or measured in sufficient detail to recognize. The Boomerang Nebula may not be entirely unique in kind, even if it currently holds the specific record for confirmed measured temperature. It may simply be the first, and so far, the most thoroughly studied example of a more general phenomenon. Stars in the midst of unusually violent late-life mass loss, briefly producing pockets of the coldest natural environments the universe is capable of generating. There is a particular kind of conceptual puzzle embedded in the Boomerang Nebula's existence that is worth sitting with carefully, because it touches on something genuinely deep about how energy and order behave in the universe, and it connects directly to the second law of thermodynamics, one of the most fundamental and most far-reaching principles in all of physics. The second law of thermodynamics, in its most commonly stated form, tells us that entropy, a measure of disorder or randomness within a closed system, tends to increase over time. Heat flows naturally from hotter objects to colder ones, never spontaneously the other way around, without the input of additional work from an outside source. This is why a hot cup of coffee left on a table gradually cools to match the temperature of the surrounding room, and why that same cup of coffee never spontaneously becomes hotter than the room around it, drawing heat in from its cooler surroundings, no matter how long you wait. At first glance, the Boomerang Nebula might seem to present a puzzle in light of this principle. Here is a region of gas that has become colder than its surroundings, colder than the cosmic microwave background radiation that bathes the entire universe. Has something violated the second law of thermodynamics? Has heat somehow flowed in the wrong direction, from a colder background into an even colder nebula, making that nebula colder still? The resolution to this apparent puzzle lies in recognizing that the Boomerang Nebula is not a simple, isolated, closed system passively exchanging heat with its surroundings until reaching equilibrium. It is an open, actively expanding system, doing genuine physical work on its surroundings as it pushes outward into the vacuum of space. The energy lost from the gas as it cools has not disappeared, and it has not violated any law of thermodynamics. It has been converted into the kinetic energy of the expansion itself, the bulk outward motion of the gas as a whole, rather than remaining in the random, disordered motion of individual molecules that we measure as a temperature. In other words, the gas is cold not because heat has flowed into it from somewhere colder, but because the gas itself has actively converted its own thermal energy into a different form of energy, the ordered, directional energy of outward bulk motion through the process of rapid adiabatic expansion. This is entirely consistent with the second law of thermodynamics, properly understood. The overall entropy of the system, including both the gas and the work it performs in pushing outward against its surroundings, continues to increase, exactly as the second law requires. The local temperature of the gas itself, however, the measure of its internal random molecular motion specifically, can and does drop below the temperature of its surroundings, precisely because that internal random motion has been systematically siphoned off and converted into the very different, much more ordered phenomenon of large-scale, directional expansion. This distinction between the disordered thermal energy that temperature measures and the ordered kinetic energy of bulk motion that does not directly register as temperature in the same way is subtle but crucial, and it is the key that resolves what might otherwise look like a genuine paradox. The Boomerang Nebula has not broken any law of physics. It has simply found an extraordinarily effective natural mechanism for converting one form of energy into another on a scale and at a speed dramatic enough to push its own internal temperature below the universal background floor that almost everything else in the cosmos settles toward. Let's take a moment to appreciate the scale of what is actually happening within the Boomerang Nebula, because the numbers involved, much like the scales we have explored in previous episodes about cosmic voids and the Great Attractor, are genuinely difficult to hold in the mind without some careful, deliberate unpacking. The central star is losing mass at a rate sufficient to shed an amount equivalent to the entire mass of the Earth roughly every few years. An absolutely staggering rate of material loss when you consider that our own Sun, over its entire multi-billion-year lifetime so far, has lost only a tiny, almost negligible fraction of its total mass to its comparatively gentle solar wind. The Boomerang Nebula's central star is doing, in the span of a human lifetime, what an ordinary star like the Sun would take unimaginably longer to accomplish through its normal, steady mass loss processes. This gas, once ejected, is moving outward at roughly 164 kilometers per second, fast enough to cross the entire distance from the Earth to the Moon in well under an hour, fast enough that, if you could somehow stand within this expanding shell of gas and watch it rush past you, the experience would bear no resemblance whatsoever to the gentle solar wind that streams past the Earth at a comparatively leisurely few hundred kilometers per second, itself already an extraordinarily fast wind by everyday human standards, but dwarfed by the violence on display in the Boomerang Nebula. The nebula itself, the visible shell of gas that has accumulated from this process over the past somewhere between 1,500 and 2,000 years, according to the most careful estimates astronomers have made, now extends across a region of space roughly half a light-year across, an almost incomprehensibly vast volume by everyday standards, and yet still small and compact by the standards of the wider cosmic structures we have explored in previous episodes, smaller than the distance between neighboring stars, let alone the vast distances between galaxies or the staggering scale of cosmic voids. Within this half-light-year-wide shell, the coldest gas, the material that has had the most time and the most room to expand and cool since being ejected from the central star, registers at that remarkable temperature of approximately 1 Kelvin. The gas closer to the central star, having had less time to expand and cool, registers at somewhat warmer temperatures, creating a kind of temperature gradient throughout the nebula, colder toward the outer edges where the gas has expanded the most, warmer toward the center where the material is more recently ejected and has had less opportunity to undergo the dramatic cooling that comes with sustained expansion. Holding all of these numbers together, a star shedding an Earth's worth of mass every few years, gas rushing outward at over 160 kilometers per second, a shell half a light year across accumulated over less than 2,000 years, cooling to within a single degree of the absolute coldest temperature that physics permits, gives us a genuine sense of just how extraordinary and how violent this particular episode of stellar death actually is, even though, from the calm, patient perspective of an observer 5,000 light-years away on Earth, it appears as little more than a faint, symmetric, gently glowing patch of light in the southern sky. It is worth pausing here to consider the location of the Boomerang Nebula within the broader context of the galaxy, much as we considered the specific galactic addresses of various habitable and hazardous zones in our previous exploration of cosmic dead zones, because location and context add further texture to this story. The Boomerang Nebula sits in the constellation Centaurus, at a distance of roughly 5,000 light-years from Earth, comfortably within the disk of the Milky Way, in a region that is not itself particularly unusual or extreme in terms of the broader galactic hazards we discussed previously. No especially elevated density of nearby supernovae, no particular proximity to the violent galactic center, nothing about its galactic neighborhood that would have predicted in advance that this particular star, among the hundreds of billions scattered throughout the Milky Way, would become the site of the coldest known natural temperature anywhere in the observable universe. This is, in its own way, a humbling and clarifying observation. The extraordinary cold of the Boomerang Nebula is not the product of some special, rare galactic location, the kind of environmental factor we spent considerable time exploring in our previous episode about cosmic dead zones and habitable zones. It is, instead, simply the product of the specific internal properties and the specific evolutionary trajectory of one particular star, an ordinary star in an ordinary location that happened to undergo an unusually dramatic and unusually compressed final act of mass loss as it approached the end of its life as a recognizable hydrogen-burning star. This matters because it suggests that the physics responsible for the Boomerang Nebula's extreme cold, the violent superwind, the rapid adiabatic expansion, the dramatic conversion of thermal energy into bulk kinetic energy, is not something that requires special cosmic circumstances to occur. It is, in principle, a phase that many ordinary stars throughout the galaxy and throughout the universe might pass through, briefly and dramatically, somewhere in the final stages of their lives, simply as a natural consequence of the physics of stellar evolution playing out, occasionally and unpredictably, in an unusually extreme and unusually rapid fashion. This raises again the tantalizing question we touched on earlier. If the Boomerang Nebula is not the product of special, rare cosmic circumstances, but simply an ordinary star caught at an ordinary location undergoing an extraordinary, but not necessarily unique phase of its evolution, how many similar objects, similarly extreme, similarly cold, might exist scattered throughout the Milky Way and other galaxies, simply waiting to be discovered by future, more sensitive instruments capable of detecting their faint, cold signatures against the backdrop of the cosmic microwave background. Let's turn our attention now to a related and equally fascinating question. What does the eventual fate of the Boomerang Nebula's gas look like as it continues to expand outward over the coming centuries and millennia? And what does this tell us about the broader life cycle of matter being recycled through the universe? As the gas ejected from the central star continues its outward journey, it will keep expanding, and as it expands, the adiabatic cooling effect that has driven its temperature down to such extraordinary lows will gradually weaken. This is a natural consequence of the physics involved. The rate of cooling associated with expansion depends on the rate of change of the gas's density, and as the gas spreads out over an ever larger volume, the density decreases more slowly in relative terms, meaning that the cooling effect, while still present, becomes progressively less dramatic over time. Eventually, as the expansion continues and as the gas spreads out across an increasingly vast volume of space, the rate of adiabatic cooling will become slower than the rate at which the surrounding cosmic microwave background radiation can warm the gas back up through simple absorption. At that point, the gas will stop cooling and will instead begin to slowly warm, asymptotically approaching the 2.7 Kelvin background temperature that represents the natural equilibrium for any sufficiently diffuse, sufficiently slowly evolving material sitting in the vacuum of space. This means that the extraordinary record-setting cold we have been discussing tonight is a genuinely temporary phenomenon, not just in the sense that the central star's extreme mass loss phase will eventually subside, but in the more specific sense that even the gas already ejected, already expanding outward and already registering that remarkable 1-degree temperature will not remain that cold forever. Over the coming centuries and millennia, as this gas continues to spread out into the surrounding interstellar medium, it will gradually warm back toward the universal background temperature, eventually losing its status as anything unusual at all, becoming, in the end, simply another diffuse cloud of enriched gas, indistinguishable in temperature from the broader interstellar medium it will eventually merge into. This temporal dimension is worth holding onto carefully, much as we held onto the temporal dimension of the great attractor's gravitational influence in a previous episode, because it reminds us that even the most extreme and most extraordinary phenomena in the universe are rarely permanent, fixed features of the cosmic landscape. They are episodes, chapters in a much longer story, dramatic and noteworthy precisely because of their temporary, transitional nature. The Boomerang Nebula's record-setting cold is a snapshot, a brief and remarkable moment in the multi-billion-year life story of a star, captured by instruments sensitive enough to detect it during the narrow window in which it happens to be true. This naturally leads us to consider what eventually becomes of all this expelled gas, beyond simply warming back toward the cosmic background temperature, and how it fits into the broader, multi-generational story of how matter cycles through stars, through interstellar space, and eventually back into new generations of stars and planets. A theme we touched on in our exploration of cosmic dead zones and the chemical enrichment of galaxies. The gas being shed by the Boomerang Nebula's central star is not simply hydrogen and helium, the primordial building blocks present since the earliest moments of the universe. Over the course of the star's multi-billion-year life, nuclear fusion processes deep within its core, and within the layers surrounding that core during the later stages of its evolution will have produced heavier elements, carbon, nitrogen, oxygen, and others, which become mixed into the outer layers of the star and are now being carried outward along with the rest of the expelled material. This means that the Boomerang Nebula, dramatic and extreme as its physical conditions are, is also participating in exactly the same fundamental process of galactic chemical enrichment that we explored in considerable detail in our previous episode about the universe's dead zones. The heavy elements being scattered outward by this particular dying star will eventually disperse into the surrounding interstellar medium, mixing with other material, other remnants from other dying stars, gradually enriching the broader galactic environment with the chemical building blocks that future generations of stars and the planets that may eventually form around them will require. In this sense, the Boomerang Nebula represents a particularly vivid and particularly dramatic example of a process that, in less extreme forms, occurs throughout the galaxy continuously as countless aging stars shed their outer layers, contributing gradually and cumulatively to the slow chemical maturation of the Milky Way as a whole. The same fundamental process responsible for producing record-breaking cold in this one specific, unusual case is also, in its more typical, gentler manifestations elsewhere throughout the galaxy, slowly building up the chemical richness that makes worlds like our own possible. There is something genuinely moving in recognizing this connection. The same physics that produces the coldest known temperature in the observable universe is also, simultaneously, contributing to the very same chemical enrichment process that, given enough time and enough generations of stellar life and death, eventually makes planets and, perhaps, life itself possible elsewhere in the galaxy. The Boomerang Nebula is not simply a curiosity, an extreme outlier sitting apart from the broader story of cosmic evolution. It is a vivid, accelerated, unusually visible example of exactly the same process that has, over billions of years, enriched our own corner of the galaxy with everything needed for a planet like Earth to exist. Let's spend some time now considering the broader scientific significance of the Boomerang Nebula, beyond its simple status as a record holder for cold temperature, because its discovery and continued study have offered genuine insight into several areas of astrophysics that extend well beyond the specific question of how cold a natural object can become. One area where the Boomerang Nebula has proven particularly valuable is in helping astronomers understand the detailed physics of how stars transition from the asymptotic giant branch phase into the planetary nebula phase, a transition that, despite occurring relatively quickly on astronomical timescales, involves complex and still not fully understood processes of mass loss, shaping, and the eventual ionization of the expelled gas by the increasingly hot, exposed stellar core left behind. The extreme conditions present in the Boomerang Nebula, the unusually fast and unusually massive outflow, have made it something of a natural laboratory for studying these processes in an unusually clear and unusually extreme form. Just as an engineer might learn more about the structural limits of a material by testing it under extreme stress rather than under gentle everyday conditions, astronomers have found that studying the Boomerang Nebula's extreme version of stellar mass loss has illuminated aspects of the underlying physics that are harder to discern in more typical, gentler examples of planetary nebula formation, where the relevant effects are present but less dramatically pronounced. The Boomerang Nebula has also proven valuable for studying the detailed shape and structure of planetary nebulae more broadly, an area of ongoing research interest because the mechanisms that transform a roughly spherical, symmetric outflow of gas into the often dramatically asymmetric, bipolar, or otherwise complexly structured shapes observed in many planetary nebulae remain an active area of investigation. The Boomerang Nebula's own distinctive hourglass or bow tie shape, visible in detailed images taken by space telescopes capable of resolving its structure with high precision, has provided valuable data for researchers working to understand exactly what combination of factors, perhaps a companion star, perhaps strong magnetic fields, perhaps the influence of a circumstellar disk, can sculpt the otherwise roughly spherical outflow of a dying star into such elaborate and asymmetric final shapes. Additionally, the techniques developed and refined to measure the Boomerang Nebula's temperature, observing the absorption of background microwave radiation by foreground molecular gas, have proven useful more broadly in studies of other cold molecular clouds throughout the galaxy, offering astronomers a powerful and sensitive method for probing the conditions within regions of space that might otherwise be difficult to study, using more conventional observational techniques that rely on detecting emitted rather than absorbed radiation. There is a particularly interesting and somewhat technical wrinkle in the Boomerang Nebula's story that deserves its own careful exploration tonight, because it concerns a refinement to our understanding of the nebula's temperature that emerged from more detailed observations conducted years after the initial 1995 discovery. And it illustrates beautifully how scientific understanding deepens and becomes more nuanced over time as better instruments and more careful analysis become available. The original 1995 measurements, which established the Boomerang Nebula's reputation as the coldest known natural object in the universe, were based on observations using ground-based radio telescopes, and they provided what was, at the time, the best available estimate of the nebula's overall temperature, approximately 1 Kelvin. This measurement was revolutionary and was widely reported, establishing the nebula's place in the popular imagination as the universe's coldest known spot. However, subsequent, more detailed observations using more sophisticated instruments, including high-resolution imaging from space-based telescopes, revealed a more complex and more nuanced picture than the original, relatively simple temperature measurement had suggested. These later observations showed that the Boomerang Nebula's structure is considerably more intricate than a simple uniform shell of expanding gas. There appears to be a dense, central hourglass-shaped region of gas, surrounded by a much larger, more extended, fainter halo of material that has been expelled over a longer period at a somewhat less extreme rate. This more detailed structural picture suggested that the very coldest temperatures, the readings approaching that remarkable 1 Kelvin mark, are likely concentrated within specific regions of the nebula, particularly in the dense, rapidly expanding central hourglass structure, where the most extreme and most recent superwind activity is concentrated, rather than being uniformly distributed throughout the entire visible extent of the nebula. Other regions, particularly the more extended outer halo, may register at somewhat warmer, though still extraordinarily cold, temperatures. This kind of refinement, where an initial, groundbreaking measurement is later understood with greater nuance and greater structural detail as observational techniques improve, is an entirely normal and entirely healthy part of how science progresses. Much as we discussed in our previous exploration of the Great Attractor, where decades of increasingly sophisticated observation gradually refined and complicated the initial, simpler picture first proposed by the Seven Samurai in 1988. The Boomerang Nebula's status as an extraordinarily cold object remains well established and scientifically robust. What has evolved, as our observational capabilities have improved, is a richer, more detailed understanding of exactly where within this complex structured object the most extreme temperatures actually occur, and how the overall thermal structure of the nebula relates to its complex, still not entirely understood physical shape. Let's take a step back now and think about the Boomerang Nebula's place within the broader landscape of extreme environments that the universe has produced, comparing it to some of the other record-holding extremes we might encounter if we surveyed the full range of conditions found throughout the observable cosmos. We have, in previous episodes, explored some of the largest structures known in the universe, the Biota's Void, hundreds of millions of light-years across and almost entirely devoid of galaxies, and the Great Attractor, a concentration of mass so large that it organizes the motion of thousands of galaxies across a supercluster spanning more than 500 million light-years. These structures represent extremes of scale, the largest examples of emptiness and of gravitational concentration that astronomers have so far identified within the observable universe. The Boomerang Nebula represents a different kind of extreme entirely, not a record for size or for gravitational influence, but a record for a specific physical property, temperature, achieved not through sheer scale, but through the specific dramatic physics of an unusually violent and unusually compressed stellar death. In this sense, it belongs to a different category of cosmic superlative than the void or the attractor, a reminder that the universe produces extremes along many different dimensions simultaneously: size, mass, temperature, density, age, each with its own particular physical mechanism responsible for pushing some specific corner of the cosmos to its observed limit. Other entries in this broader catalogue of cosmic extremes might include the hottest known temperatures found in the cores of the most massive stars or in the immediate aftermath of supernova explosions, where temperatures can reach billions of degrees, utterly dwarfing anything achievable in earthly laboratories or experienced anywhere else in more typical astronomical environments. They might include the densest known objects, the neutron stars left behind by certain kinds of supernovae, where matter is compressed to such extraordinary densities that a single teaspoon's worth would weigh, on Earth, more than a mountain. They might include the most powerful known explosions, the gamma-ray bursts we discussed in our exploration of cosmic dead zones, capable of outshining an entire galaxy for a brief, intense moment. Setting the Boomerang Nebula's extreme cold alongside these other cosmic extremes helps illustrate something important about the nature of physical law and the nature of the universe more broadly. That the same fundamental rules of physics applied to different specific circumstances, different masses, different velocities, different geometries, can produce an extraordinarily wide range of outcomes, from the almost unimaginable heat of a supernova's core to the almost unimaginable cold of a rapidly expanding stellar wind, each one representing in its own particular domain a kind of natural record, a demonstration of just how far the ordinary laws of physics can be pushed when the right specific circumstances happen to align. There is a thought experiment worth walking through carefully tonight, because it helps make the abstract physics of adiabatic cooling considerably more tangible and considerably easier to hold on to. Much as our earlier comparisons between galactic scales and human scales helped make the size of the Bowser's void more comprehensible. Imagine, for a moment, a balloon filled with compressed air, the kind of high-pressure air contained within a scuba tank or a bicycle pump's reservoir. When you release that compressed air suddenly, allowing it to expand rapidly into the surrounding atmosphere, the expanding air cools noticeably, a phenomenon you can feel directly if you have ever held your hand near the nozzle of a can of compressed air used for cleaning electronics, feeling the chill of the rapidly expanding gas against your skin. Now, imagine scaling up this same basic process by an almost unimaginable factor. Instead of a small canister of compressed air, imagine the entire outer envelope of a star, a region of gas many times more massive than the entire planet Earth, suddenly being released from the gravitational compression that had held it in place for the star's entire previous lifetime, and allowed to expand outward, not into a room at ordinary atmospheric pressure, but into the near-perfect vacuum of interstellar space, where there is essentially no surrounding pressure at all to resist or slow that expansion. In this scaled-up scenario, the cooling effect that you feel as a faint chill against your skin when using a can of compressed air becomes, instead, a cooling effect powerful enough to drive the temperature of an entire stellar envelope down to within a single degree of the absolute coldest temperature that physics permits anywhere in the universe. The basic physical principle is identical in both cases: expanding gas, converting its own thermal energy into the kinetic energy of bulk motion, and thereby cooling itself in the process. What differs is simply the scale, the mass of gas involved, the speed of the expansion, and the near total absence of any surrounding pressure to resist that expansion in the vacuum of space, compared to the modest resistance offered by ordinary atmospheric pressure here on Earth. This comparison, modest as it might initially seem, between a can of compressed air and the death throes of an entire star, captures something genuinely important about how the universe so often operates. The same basic physical principles that govern small everyday phenomena here on Earth also govern the most extreme and most extraordinary events occurring throughout the cosmos, differing not in kind, but simply in scale, in the sheer magnitude of mass, energy, and distance involved. The Boomerang Nebula is not powered by some exotic unknown physics unique to the depths of space. It is powered by exactly the same basic thermodynamics you might encounter in a vastly gentler form in your own kitchen or garage, scaled up by factors so enormous that the resulting effect becomes record-breaking rather than merely a mild curiosity. Let's turn our attention now to a question that naturally arises from everything we have discussed so far. Are there other candidates beyond the Boomerang Nebula for extraordinarily cold natural environments elsewhere in the universe, and how confident can we actually be that the Boomerang Nebula genuinely represents the single coldest such environment currently known? In the years since the Boomerang Nebula's extreme temperature was first established, astronomers have continued to search for and study other planetary nebulae and other objects undergoing similarly dramatic, rapid mass loss episodes, in part specifically to determine whether any other objects might rival or even exceed the Boomerang Nebula's remarkable cold. This search has, to date, not turned up any confirmed rival that clearly surpasses the Boomerang Nebula's measured temperature, and it retains its informal title as the coldest known natural place in the observable universe, a title it has now held for roughly 3 decades. That said, the search itself has revealed a number of other planetary nebulae and pre-planetary nebulae exhibiting unusually fast and unusually massive outflows, suggesting that the basic phenomenon responsible for the Boomerang Nebula's extreme cold, violent, rapid mass loss during the final stages of certain stars' transition from the asymptotic giant branch toward becoming a planetary nebula may not be entirely unique to this one specific object, even if the Boomerang Nebula currently represents the most extreme, most thoroughly documented example identified so far. This raises an interesting possibility that is worth holding on to with appropriate scientific humility. The Boomerang Nebula's record may simply reflect the limits of our current observational capability and the relatively limited number of objects that have been studied with sufficient detail and sufficient sensitivity to allow a precise temperature measurement, rather than reflecting some genuine, unique physical extremity that sets the Boomerang Nebula apart from every other similar object in the galaxy or the wider universe. There may well be other, similarly cold, or even colder objects scattered throughout the Milky Way and other galaxies, simply waiting for sufficiently sensitive future instruments to identify and measure them with the same care and precision that revealed the Boomerang Nebula's remarkable temperature. This uncertainty is not a weakness in our current understanding, but rather an honest reflection of the genuine limits of observational astronomy, where any claim about a record-holding extreme object is necessarily a claim about the most extreme example we have so far been able to identify and measure, rather than a claim about some absolute, definitively confirmed limit across the entire universe. As we discussed in our exploration of cosmic dead zones, science at the frontier of the knowable often involves exactly this kind of careful, qualified claim, confident in the specific result obtained through careful measurement, but appropriately humble about whether that result represents the final word on the broader question being investigated. Let's consider, for a few moments, what future observations and future instruments might reveal about the Boomerang Nebula specifically, and about the broader population of extremely cold cosmic environments more generally, much as we considered the future of great attractor research and cosmic dead zone mapping in our previous explorations. The next generation of radio and submillimeter telescopes, including increasingly sensitive arrays capable of detecting extremely faint molecular emission and absorption signatures, promise to allow astronomers to study the detailed temperature structure of objects like the Boomerang Nebula with considerably greater precision and considerably greater spatial resolution than was available even in the more detailed follow-up observations conducted in the years after the original 1995 discovery. These improved capabilities should allow researchers to map out, in much finer detail, exactly how the temperature varies throughout the different regions of the Boomerang Nebula, from the dense, rapidly expanding central hourglass structure to the more extended, slower-moving outer halo, providing a much more complete and much more precise picture of the nebula's overall thermal structure than the somewhat simplified single-temperature estimate that first established its remarkable reputation in the mid-1990s. Beyond the Boomerang Nebula itself, improved instrumentation should also allow astronomers to conduct much more comprehensive surveys of other planetary nebulae and pre-planetary nebulae throughout the Milky Way, searching specifically for other examples of the kind of violent, rapid mass loss episode responsible for the Boomerang Nebula's extreme cold. This kind of systematic survey could help answer the question we raised a moment ago, whether the Boomerang Nebula's extreme temperature represents a genuinely rare, perhaps even unique physical extremity, or whether it is simply the first and most thoroughly studied example of a more common, if still relatively brief and relatively rare, phase that many dying stars throughout the galaxy might pass through. There is also considerable ongoing interest in studying the detailed mechanisms responsible for shaping planetary nebulae into their often dramatically asymmetric bipolar forms, the same mechanisms that may be responsible for the Boomerang Nebula's distinctive hourglass shape. Improved imaging capabilities, combined with improved theoretical modeling of the complex fluid dynamics and magnetic field interactions involved in shaping an expanding stellar outflow, may eventually allow astronomers to understand, with much greater confidence, exactly why some dying stars produce simple, roughly spherical planetary nebulae, while others, including the Boomerang Nebula, produce much more elaborate, much more dramatically structured final shapes. Each of these future research directions promises to deepen and refine our understanding of the specific phenomenon we have been exploring tonight, much as the ongoing refinement of great attractor measurements and cosmic habitability mapping continues to deepen our understanding of those previously explored topics. The Boomerang Nebula's story, like so many of the cosmic stories we explore together on this channel, remains an active, ongoing area of scientific investigation, with new chapters likely to be written as observational technology continues to advance. There is a philosophical dimension to the Boomerang Nebula's existence that is worth sitting with carefully before we begin to draw our exploration tonight toward its close, one that touches on the relationship between extremity and ordinariness in how the universe operates. We have spent this evening exploring an object that represents, by a meaningful margin, the most extreme example of a particular physical property, cold, that has so far been identified anywhere in the observable universe. And yet, as we discovered in walking through the underlying physics, this extreme outcome arises not from some exotic, unprecedented physical process unique to this one specific location, but from the same basic principles of thermodynamics and gas expansion that govern phenomena as mundane and as everyday as a can of compressed air releasing its contents in an ordinary household setting. This pattern, where extraordinary cosmic outcomes emerge from the straightforward application of ordinary physical principles, simply scaled up to extraordinary magnitudes of mass, energy, distance, or time, is one of the recurring and genuinely beautiful themes we have encountered again and again across our explorations together on this channel. The largest known void in the universe emerges from the same basic gravitational physics responsible for the clustering of any two nearby masses. The motion of our entire galaxy toward a distant concentration of matter emerges from the same basic gravitational attraction responsible for an apple falling from a tree. And now, the coldest known natural temperature in the observable universe emerges from the same basic thermodynamic principle responsible for the chill you feel when releasing pressurized air from a small canister. There is something genuinely reassuring in recognizing this pattern, a reminder that the universe, vast and strange and full of genuinely extraordinary phenomena as it is, does not require an equally vast and extraordinary set of entirely separate physical laws to produce those phenomena. The same comparatively small, comparatively comprehensible set of fundamental physical principles, gravity, thermodynamics, electromagnetism, and a handful of others, operating consistently across every scale from the smallest laboratory experiment to the largest cosmic structure, is responsible for the entire breathtakingly varied range of phenomena the universe has produced, from the gentle warmth of a sunlit afternoon to the violent heat of a supernova's core, from the everyday chill of an autumn evening to the record-breaking cold of a dying star's expanding envelope, 5,000 light-years away, hovering at the very edge of what temperature itself is theoretically capable of becoming. Let's spend a few more moments considering what it might actually feel like, in some imaginative sense, to encounter the conditions present within the Boomerang Nebula directly, much as we imagined standing within the interior of the Booter's Void in a previous episode, recognizing, of course, that no human observer, and indeed no physical object as we understand them, could survive such an encounter in any literal sense. If you could somehow find yourself within the coldest regions of the Boomerang Nebula's expanding gas, the experience would bear almost no resemblance to cold as we understand and experience it here on Earth. The gas within the nebula, despite its extraordinarily low temperature, is also extraordinarily diffuse, far less dense than even the thinnest air found at the highest reaches of Earth's atmosphere. This means that the experience of being immersed in this gas would not resemble being submerged in extremely cold water or exposed to an extremely cold wind, sensations that depend on a relatively dense medium efficiently conducting heat away from a warmer object immersed within it. Instead, the primary hazard of finding yourself in such an environment would likely come not from conductive heat loss through contact with the surrounding cold gas, but from the simple, stark fact of being in the vacuum of space at all, far from any source of warmth, air, or pressure, a hazard that would apply equally whether the surrounding gas happened to be at 1 Kelvin or at the more typical 2.7 Kelvin background temperature of ordinary deep space. The specific extremity of the Boomerang Nebula's temperature, remarkable as it is from a scientific perspective, would, in this sense, be almost a secondary consideration compared to the much more immediate and much more universal hazards of finding oneself unprotected in the vacuum of interstellar space at any temperature at all. This is, in its own way, a useful corrective to the imaginative exercise, a reminder that the Boomerang Nebula's extreme cold, while genuinely remarkable and genuinely record-breaking from a scientific and physical perspective, exists within a context, the near-perfect vacuum of space, that would already be lethal to any unprotected human observer regardless of the specific temperature involved. The wonder of the Boomerang Nebula lies not in some uniquely intensified version of the cold we experience on a winter night here on Earth, but in the specific, measured fact that the gas within it has reached a temperature lower than the rest of the universe's ambient background. A genuinely strange and genuinely noteworthy physical fact, even though its practical sensory experience were such an experience even possible, would likely be dominated by the much more immediate and much more familiar hazards of the vacuum itself, rather than by any uniquely intensified sensation of cold. Having explored the physics, the history, the scientific significance, and even the imaginative texture of the Boomerang Nebula in considerable detail, let's turn our attention to drawing together some of the broader threads of tonight's exploration, much as we did in the closing portions of our previous episodes on the Booter's Void, the Great Attractor, and the universe's cosmic dead zones. The Boomerang Nebula teaches us something valuable about the relationship between expectation and discovery in science. Before its temperature was measured in detail, there was a reasonable, well-grounded expectation based on the established physics of the cosmic microwave background that nothing in the natural universe should be able to sit colder than that universal 2.7 Kelvin floor. The Boomerang Nebula's measured temperature of approximately 1 Kelvin directly challenged that expectation, not by revealing some flaw in the underlying physics of the cosmic microwave background, which remains exactly as well established and exactly as well understood as it was before the Boomerang Nebula's discovery, but by revealing a previously underappreciated mechanism, the dramatic adiabatic cooling associated with sufficiently rapid and sufficiently massive gas expansion, capable of locally and temporarily overcoming that universal background warming effect. This is precisely the kind of discovery that makes observational astronomy, and indeed the broader scientific enterprise, so consistently rewarding. Not the overturning of well-established physical principles, which happens only rarely and only with overwhelming evidence, but the discovery of new, previously unrecognized ways in which those well-established principles can combine and interact to produce genuinely surprising, genuinely record-breaking outcomes in specific unusual circumstances. The laws of thermodynamics remain exactly as valid and exactly as universal as they were before 1995. What changed with the Boomerang Nebula's discovery was simply our appreciation for just how dramatically those laws could be pushed by a sufficiently extreme natural process, the violent superwind of a dying star, shedding mass at a rate and at a velocity considerably beyond what had previously been observed or anticipated in more typical planetary nebulae. There is a particular kind of cosmic humility that emerges from sitting with the Boomerang Nebula's story for an extended period, and it connects in an interesting way to some of the reflections we offered in our previous exploration of the universe's many dead zones. In that earlier episode, we considered how fortunate and how specific our own circumstances are, here on Earth, orbiting a stable, long-lived star in a quiet, chemically enriched region of the galaxy, far from the most violent and most hazardous cosmic environments. Tonight, in exploring the Boomerang Nebula, we have encountered a rather different kind of cosmic circumstance, an environment defined not by violence and hazard in the sense we explored previously, supernovae, gamma-ray bursts, crowded cluster cores, but by an entirely different and in some ways equally extreme physical condition. A cold so profound that it approaches the theoretical limits of what temperature itself is capable of becoming anywhere in the universe. And yet, even this extreme cold, like the various hazards we explored in our previous episode, exists within a much broader context of cosmic ordinariness. The star responsible for producing the Boomerang Nebula was, for most of its multi-billion-year existence, an entirely unremarkable star, going about the ordinary business of nuclear fusion in much the same way as the hundreds of billions of other stars scattered throughout the Milky Way. It is only in this particular, brief, dramatic final phase of its life, a phase lasting perhaps a few thousand years out of a total stellar lifetime likely measured in billions of years, that this star has produced anything resembling a genuine cosmic record, the coldest known natural temperature anywhere in the observable universe. This offers a particular kind of perspective worth carrying forward. That extraordinary, record-breaking phenomena in the universe are often not permanent, defining features of the objects that produce them, but rather brief, dramatic episodes embedded within much longer, much more ordinary histories. The Boomerang Nebula's central star spent billions of years being an unremarkable, ordinary star before this brief flourish of extreme activity, and the gas it has so dramatically and so coldly expelled will, in turn, spend a far longer subsequent period gradually warming back toward the universal background temperature and eventually merging indistinguishably into the broader interstellar medium of the galaxy. The record-breaking moment we have spent this evening exploring is a genuine, real, scientifically significant moment. But it is also, in the much longer arc of this star's and this gas's full history, a remarkably brief one. Let's consider, for a final extended stretch of tonight's exploration, what the Boomerang Nebula might suggest about the broader question of extremity within the universe more generally, and how thinking carefully about one specific cosmic record can illuminate something about the nature of cosmic records in general. Throughout our explorations on this channel, we have encountered a recurring pattern. The universe, across its vast extent and its vast age, regularly produces specific examples of extreme physical conditions: the largest known void, the most massive known concentration of gravitating matter in our local supercluster, and now, the coldest known natural temperature, each one representing in its own specific physical dimension an outcome that pushes against the boundaries of what the underlying physical laws permit. What is interesting about each of these examples, when considered together, is that none of them represents some kind of unprecedented violation or exception to ordinary physical law. Each one represents instead an unusually extreme but entirely lawful outcome produced by ordinary physical processes, gravity, thermodynamics, the gradual evolution of cosmic structure, operating under unusually extreme circumstances, an unusually large initial density fluctuation in the case of the void, an unusually massive concentration of matter in the case of the great attractor, an unusually violent and unusually rapid stellar mass loss episode in the case of the Boomerang Nebula. This suggests a broader principle about how to think about cosmic superlatives and cosmic records more generally. That the universe, given sufficient time, sufficient scale, and sufficient opportunity, will naturally tend to produce examples that approach the boundaries of what its own physical laws allow, not through any special exception to those laws, but simply through the ordinary operation of probability and physics across an almost unimaginably vast number of opportunities, an almost unimaginably vast number of stars, an almost unimaginably vast volume of space, and an almost unimaginably long span of cosmic time. Given enough rolls of the dice, even genuinely rare and genuinely extreme outcomes will eventually occur somewhere, and our own observational instruments, increasingly sensitive and increasingly far-reaching with each passing decade, have begun to catch these rare outcomes in the act. The largest void, the most massive nearby attractor, the coldest known natural temperature, each one a kind of testament to just how thoroughly the universe explores the full range of possibilities that its own underlying physical laws make available to it. As we begin to bring tonight's exploration toward its close, let's return, one final time, to the specific concrete image of the Boomerang Nebula itself, 5,000 light-years away, in the constellation Centaurus, its faint, symmetric lobes glowing gently against the darkness of the surrounding sky, utterly unremarkable in its outward visual appearance, and yet harboring, within its expanding gas, a physical extremity that took careful, patient scientific investigation to uncover and to properly understand. There is something fitting in the fact that this particular cosmic record, unlike the dramatic visual spectacle of a supernova or the overwhelming gravitational influence of the great attractor, reveals itself not through any obvious visual drama, but through the patient, careful measurement of a property, temperature, that cannot be seen directly at all, only inferred through the careful analysis of how specific molecules within the nebula's gas interact with the universe's own ancient background radiation. The coldest place in the known universe announces itself not with a dramatic flash of light, but with a subtle, easily overlooked absence, a slight, careful dip in in an otherwise uniform background glow, requiring sensitive instruments and careful analysis to detect and to properly interpret. This feels, in its own way, like a fitting metaphor for much of what we explore together on this channel, that some of the universe's most remarkable and most genuinely surprising features reveal themselves not through obvious spectacle, but through patient, careful attention to subtle details that might, on first glance, seem unremarkable. The Boomerang Nebula looked for years like simply another modest planetary nebula among the many thousands catalogued throughout the galaxy, distinguished mainly by its evocative boomerang-like shape. It took careful, patient radio astronomy, looking specifically for the subtle signature of absorbed background radiation, to reveal that this particular, otherwise unremarkable-looking object was quietly holding a genuine cosmic record, hidden within its gently expanding gas. Let's hold, for these final moments of tonight's exploration, the full image of what we have discovered together this evening, drawing the various threads into something resembling a single, coherent understanding. A star, ordinary for billions of years, entered the final dramatic stages of its life and began shedding its outer layers with extraordinary speed and extraordinary intensity, far beyond the more typical, gentler mass loss exhibited by most dying stars of similar type. This rapid, massive outflow of gas, rushing outward into the vacuum of space at over 160 kilometers per second, underwent a powerful adiabatic cooling effect, converting its own thermal energy into the kinetic energy of bulk expansion, driving its temperature down to approximately 1 Kelvin, colder than the 2.7 Kelvin cosmic microwave background that bathes the entire rest of the observable universe in its ancient, gentle warmth. This cooling, dramatic and extreme as it is, does not violate any law of physics. It represents, instead, a particularly vivid and particularly extreme demonstration of exactly how powerful the ordinary physics of expansion cooling can become when scaled up to the size of an entire dying star's envelope, a demonstration that the universe, given the right specific circumstances, an unusually massive and unusually rapid stellar superwind, is capable of locally and temporarily producing temperatures colder than its own ambient background radiation. A possibility that, before the Boomerang Nebula's discovery in the mid-1990s, had not been clearly recognized or anticipated by the broader astronomical community. This remarkable cold is, in the end, a temporary transitional phenomenon, destined to fade as the central star's extreme mass loss episode eventually subsides, and as the already expelled gas continues its outward journey, gradually warming back toward the universal background temperature over the coming centuries and millennia, eventually merging indistinguishably into the broader interstellar medium of the galaxy, carrying with it the heavy elements forged within the star's interior, contributing, in its own small way, to the same long, slow process of galactic chemical enrichment that we explored in considerable detail in our previous episode about the universe's habitable and inhospitable zones. And throughout all of this, the underlying physics remains exactly what it has always been, the same thermodynamics responsible for the chill of a compressed air canister, the same basic principles that govern phenomena both extraordinarily mundane and extraordinarily extreme, scaled up in this one particular case to produce a result genuinely worthy of the description we have used throughout tonight's exploration. A place that, by the ordinary expectations we carry about the universe's coldest possible ambient conditions, simply shouldn't exist, and yet does, quietly, patiently, 5,000 light-years away, waiting to be discovered by anyone curious enough and careful enough to look. The night has settled further now, and the image of that distant, impossibly cold nebula, glowing faintly in the southern sky, can begin to recede into the quiet background of your awareness, not as a source of unease, but as a small, precious piece of cosmic strangeness to carry gently into sleep. 5,000 light-years away, a dying star continues its dramatic, rapid shedding of mass, gas rushing outward into the vacuum at speeds that would be utterly unimaginable in any everyday context, cooling as it expands to within a single degree of the absolute coldest temperature the universe is capable of producing anywhere, a temperature colder than the ancient afterglow of the Big Bang itself, colder than the supposed universal flaw that bathes every other corner of the observable cosmos in its gentle, ambient warmth. And here, wherever you happen to be resting tonight, warm beneath your blankets or settled comfortably into your chair, the contrast between your own immediate surroundings and that distant, extraordinary cold could hardly be more complete. You are, at this very moment, warmer by hundreds of degrees than the coldest known place in the observable universe, a comparison that, when held quietly in mind, can offer its own small, particular kind of comfort. A reminder of just how gentle, just how hospitable, just how thoroughly warmed by the steady light of a nearby, stable star your own specific corner of the cosmos actually is. If tonight's journey toward the universe's coldest known place has left you with something worth carrying into rest, a quiet appreciation for the strange, beautiful, lawful extremity that the cosmos is capable of producing, you are always welcome back at Beyond the Cosmos, whenever curiosity calls you toward another of the universe's remarkable questions. There is always another corner of the cosmos waiting to be explored, always another patient, careful measurement waiting to reveal some new, unexpected facet of how the universe actually operates. For now, let the cold recede into the distance where it belongs, 5,000 light-years away, fading gradually, as it always was destined to do, back toward the gentle, ordinary warmth of the universe's ancient background glow. And let your own warmth, here, now, in this specific comfortable moment, be enough. There is a particular thread in this story that we have only touched on briefly so far, and that deserves a more careful, sustained exploration. The question of how astronomers distinguish between different molecular traces when studying an object like the Boomerang Nebula, and why the specific choice of carbon monoxide as the primary tool for measuring its temperature turned out to be so important to the discovery itself. Molecular astronomy, the branch of astrophysics concerned with detecting and analyzing the specific signatures of molecules in space, relies on the fact that different molecules absorb and emit radiation at very specific, well-characterized wavelengths, determined by the quantum mechanical structure of the molecule itself, the specific ways its electrons can be arranged, and the specific ways the molecule itself can rotate and vibrate. Carbon monoxide, a simple molecule made of one carbon atom bonded to one oxygen atom, happens to be one of the most useful and most widely studied molecules in this context because it is relatively abundant in many astrophysical environments and because its rotational transitions, the specific quantum jumps it makes between different states of rotational motion, produce radiation at wavelengths that are both readily detectable with existing radio telescope technology and sensitively dependent on the surrounding physical conditions, including temperature and density. When astronomers observe carbon monoxide molecules within an expanding shell of gas, like the one surrounding the Boomerang Nebula's central star, they can use the precise pattern of absorption or emission across multiple different rotational transitions to build up a detailed picture of the physical conditions within that gas, including not just its overall temperature, but how that temperature varies with distance from the central star, how the density of the gas varies, and how the velocity of the expanding material changes as a function of distance and time since ejection. This technique, sometimes called molecular line astronomy, has become an indispensable tool throughout modern astrophysics, used not just for studying dying stars like the one at the heart of the Boomerang Nebula, but for studying the dense molecular clouds where new stars are actively forming, for studying the chemistry of comets within our own solar system, and for studying the atmospheres of other planets, both within our solar system and increasingly, as detection techniques continue to improve, around other stars entirely. The specific application that revealed the Boomerang Nebula's extraordinary cold represents one particularly striking and particularly well-known example of this broader technique's power. But it sits within a much larger tradition of using molecular signatures as a kind of universal diagnostic tool, allowing astronomers to infer detailed physical conditions in environments that would otherwise remain entirely inaccessible to direct measurement. Let's spend some additional time considering the broader category of objects that the Boomerang Nebula belongs to, pre-planetary nebulae, and the closely related, slightly more evolved planetary nebulae proper, because understanding this broader family of objects helps contextualize just how unusual the specific case we have been exploring tonight actually is. As we discussed earlier, the transition from a star's red giant or asymptotic giant branch phase into its final planetary nebula phase typically involves a complex sequence of events, beginning with a gradual increase in the rate of mass loss as the star's outer envelope becomes progressively more loosely bound, continuing through a phase of particularly intense mass loss, sometimes called a superwind, and culminating in the exposure of the star's hot, compact core, which then ionizes the previously expelled gas, causing it to glow visibly and producing what astronomers classify as a true planetary nebula, distinguished from the earlier pre-planetary or protoplanetary phase by this visible ionization and glow. The Boomerang Nebula appears to occupy a particularly interesting position within this evolutionary sequence, generally classified by researchers as a pre-planetary nebula, or in some classification schemes, a young or protoplanetary nebula, meaning that the central star has not yet become hot enough to fully ionize the surrounding expelled gas, which is why the nebula's visible glow, while detectable, is comparatively faint, and why the dramatic temperature measurements that established its reputation came not from observations of glowing ionized gas, but from radio observations of the cold, largely neutral molecular gas in its outer regions. This classification matters because it tells us something important about the specific timing of the Boomerang Nebula's discovery relative to its host star's ongoing evolution. We are observing this object at a particularly early, particularly dramatic stage of its transition from dying giant star to fully formed planetary nebula, a stage during which the most intense and most rapid mass loss is actively occurring. But before the central star has yet become hot and exposed enough to begin the ionization process that will eventually transform the nebula's appearance considerably, causing it to glow more brightly and more distinctly as the increasingly exposed stellar core's intense ultraviolet radiation begins to interact more directly with the surrounding gas. Other objects within this same broader category of pre-planetary and young planetary nebulae have been studied by astronomers specifically to understand how common or how rare the kind of extreme, rapid mass loss episode responsible for the Boomerang Nebula's record-breaking cold actually is. Some other objects have shown evidence of similarly fast outflows, though none, to date, have been measured with quite the same combination of extreme outflow speed, extreme mass loss rate, and resulting extreme cold that the Boomerang Nebula displays, reinforcing its continued status as a particularly extreme, if perhaps not entirely unique, example of this broader category of dramatic stellar transition. There is a related question worth exploring carefully, one that touches on the broader astrophysical puzzle of exactly what causes some dying stars to undergo this kind of unusually intense, unusually rapid superwind phase, while other, Seemingly similar stars proceed through a much gentler, much more gradual transition into their own eventual planetary nebula phase. This remains, it must be said, an area of active and ongoing research without a single, simple, universally agreed upon explanation. Several different factors have been proposed by researchers studying this question, and it is likely that the truth involves some combination of multiple contributing causes rather than any single isolated mechanism. One frequently discussed possibility involves the presence of a binary companion star, a second star gravitationally bound to the dying giant, whose presence and whose specific orbital configuration relative to the primary star could, in principle, dramatically influence the rate and the geometry of mass loss from the primary star's expanding outer envelope. Some researchers studying the Boomerang Nebula specifically have proposed that an unseen companion star, perhaps itself a smaller, fainter star, or even a compact stellar remnant, might be interacting gravitationally with the primary star's expanding outer layers in a way that helps explain both the unusually rapid rate of mass loss and the unusually structured hourglass-like shape that the resulting nebula has taken. Another possibility involves the role of magnetic fields, generated either by the dying star itself or by interactions between the star and any surrounding material, potentially helping to channel and accelerate the outward flow of expelled gas in ways that a purely spherical, magnetically uninfluenced outflow would not naturally produce. Magnetic fields are notoriously difficult to measure directly in these kinds of astrophysical environments, but their potential influence on the shape and the dynamics of stellar outflows has become an increasingly important area of theoretical and observational investigation in recent years. A third possibility involves the specific internal structure and specific evolutionary history of the dying star itself, including factors like its original mass, its rotation rate, and the detailed internal physics of how energy is transported from its core to its surface during the final, unstable stages of its life as an asymptotic giant branch star. Stars with slightly different masses, slightly different rotation rates, or slightly different internal structures might naturally produce somewhat different patterns and somewhat different intensities of mass loss as they approach the end of this particular evolutionary phase, even if the broad outlines of their evolution are otherwise quite similar. Untangling exactly which of these factors, or what combination of factors, is responsible for the Boomerang Nebula's particularly extreme and particularly well-documented superwind remains an open area of investigation, one that connects this specific object's story to much broader questions in stellar astrophysics about the diversity of pathways that stars of generally similar mass and generally similar evolutionary stage can nonetheless follow as they approach the ends of their respective lives. Let's turn our attention, for a substantial stretch of tonight's exploration, to the broader concept of absolute zero itself, because we touched on it earlier in our discussion, but have not yet fully explored just how remarkable and just how carefully studied this particular physical limit has become, both in laboratory settings here on Earth and in the broader theoretical framework of modern physics. The pursuit of extremely low temperatures has been a major and surprisingly rich area of experimental physics for well over a century, beginning with the gradual liquefaction of various gases, including, eventually, helium, which remains a liquid down to temperatures only a few degrees above absolute zero, lower than almost any other substance under normal pressure conditions. Each successive achievement in this pursuit of cold, liquefying hydrogen, then liquefying helium, then achieving temperatures within a fraction of a degree of absolute zero using increasingly sophisticated techniques, represented a genuine triumph of careful experimental physics, requiring researchers to develop entirely new technologies and entirely new theoretical frameworks to understand and to achieve each successive milestone. Modern laboratory techniques, including methods like laser cooling and magnetic trapping, have allowed physicists to cool small samples of certain atoms to temperatures within a tiny fraction of a billionth of a degree above absolute zero. Astonishingly, almost unimaginably close to the theoretical floor. Though, as we discussed earlier, never quite reaching that floor exactly, in accordance with the third law of thermodynamics. These extraordinarily cold laboratory samples have revealed entirely new and entirely unexpected phenomena, including exotic states of matter like Bose-Einstein condensates, in which a large collection of atoms, cooled to nearly absolute zero, begins to behave collectively as a single unified quantum entity, rather than as a collection of separate individual particles. A phenomenon with no everyday analog, and one that only becomes observable at temperatures far colder than anything found naturally anywhere on the surface of the Earth. It is worth noting, and this is a genuinely interesting point of comparison, that these laboratory-achieved temperatures, the extraordinarily cold samples produced through decades of careful experimental refinement here on Earth, are in fact considerably colder than the Boomerang Nebula's remarkable, but still comparatively much warmer temperature of approximately 1 Kelvin. In this specific narrow sense, human laboratories have achieved temperatures colder than the coldest known naturally occurring place in the observable universe, a distinction worth being precise about as we continue our exploration tonight. The Boomerang Nebula's significance, then, lies not in being colder than anything achieved anywhere, including human laboratories, but specifically in being the coldest known natural environment, the coldest place that the universe itself has produced without any deliberate engineering or experimental intervention, through the unaided ordinary operation of stellar physics and thermodynamics playing out across an entire dying star's outer envelope. This distinction between the coldest achieved temperature overall and the coldest naturally occurring temperature specifically is an important one, and it adds an interesting layer of nuance to the title we have been using throughout tonight's exploration. This distinction between engineered and natural cold opens up an interesting avenue for further reflection, one that connects to broader questions about the relationship between human technological achievement and the universe's own unaided capabilities. Human laboratories achieving temperatures colder than the Boomerang Nebula represent a genuinely impressive feat of careful, deliberate engineering, involving sophisticated technologies like laser cooling, where carefully tuned beams of light are used to systematically remove kinetic energy from individual atoms, and magnetic trapping, where precisely controlled magnetic fields are used to confine and further cool already extremely cold atomic samples. These techniques require not just advanced technology, but also an extraordinarily detailed theoretical understanding of atomic physics and quantum mechanics, the kind of understanding that took centuries of careful scientific investigation, building from the earliest studies of thermodynamics through to the full development of quantum theory in the 20th century, to achieve. The Boomerang Nebula, by contrast, achieves its remarkable cold through no deliberate engineering or intentional process whatsoever. It is simply the natural, unintended consequence of ordinary stellar physics, the gravitational instability of a dying star's outer envelope, the violent, rapid mass loss that results, and the straightforward, well-understood thermodynamics of gas expansion, all operating according to physical laws that would apply equally whether or not any conscious observer ever existed to measure or to appreciate the result. There is something worth sitting with in this contrast. The universe, operating through entirely unintentional, entirely undirected physical processes, has nonetheless managed to produce, in this one particular case, a result that approaches remarkably close to the same physical extremity that human scientists, through centuries of careful, deliberate, intentional research and engineering have also managed to achieve, albeit through an entirely different mechanism and to an even more extreme degree. This suggests something interesting about the relationship between intention and outcome in physical processes. That the same fundamental laws of physics, whether harnessed deliberately by careful human experimentation or simply playing out unintentionally through the ordinary, undirected evolution of a dying star, can produce remarkably similar kinds of extreme results. Each pathway, the engineered and the natural, representing a different but equally valid demonstration of just how far the universe's fundamental physical principles can be pushed toward their ultimate theoretical limits. Let's turn our attention now to a slightly different but closely related topic: the broader question of how cold environments, both natural and artificial, have proven scientifically useful throughout the history of physics, and how the study of extreme cold connects to some of the most important and most far-reaching discoveries in modern science. The behavior of matter at extremely low temperatures has revealed some of the most genuinely surprising and counterintuitive phenomena in all of physics. Phenomena that simply do not manifest at the more moderate temperatures we experience in everyday life, because the thermal jostling of atoms and molecules at ordinary temperatures tends to mask or disrupt the more subtle quantum mechanical behaviors that become dominant and become directly observable only when that thermal jostling is sufficiently reduced. Superconductivity, the phenomenon in which certain materials, when cooled below a specific critical temperature, lose all electrical resistance entirely, allowing electric current to flow through them indefinitely without any energy loss whatsoever, was first discovered in the early 20th century through careful experiments involving extremely cold liquid helium. And it remains, more than a century later, an area of active and important research with potential applications ranging from extremely powerful electromagnets used in medical imaging and particle accelerators to the possibility, still being actively pursued, of developing materials that exhibit this remarkable property at temperatures closer to those found in everyday environments, which would have transformative implications for energy transmission and storage, if ever achieved. Superfluidity, a closely related phenomenon in which certain liquids, when cooled to sufficiently low temperatures, lose all internal friction entirely, allowing them to flow without any resistance whatsoever, even climbing up and over the walls of their containers in apparent defiance of ordinary gravity, was likewise first discovered and studied through careful experiments involving extremely cold liquid helium, revealing behavior so strange and so counterintuitive that it took physicists considerable time to develop a full theoretical understanding of exactly what was happening at the quantum mechanical level. These discoveries, achieved through the patient, careful pursuit of extreme cold in laboratory settings here on Earth, illustrate a broader and genuinely important principle in physics, that pushing any physical system toward an extreme condition, whether extreme heat, extreme pressure, extreme density, or, as in this case, extreme cold, often reveals entirely new physical phenomena that remain hidden and undetectable under more ordinary, moderate conditions. The Boomerang Nebula, in its own way, represents a kind of natural laboratory for this same broader principle, an environment where the universe's own physical processes have pushed temperature toward its ultimate theoretical limit, offering astronomers a genuinely unique opportunity to study molecular behavior and gas dynamics under conditions that would be exceptionally difficult, if not impossible, to replicate using laboratory techniques here on Earth, where achieving such extremely cold temperatures across a volume of gas as large as the Boomerang Nebula's expanding envelope would be entirely beyond any currently conceivable experimental capability. Let's spend some time now considering the broader implications of the Boomerang Nebula's discovery for our understanding of stellar evolution more generally, returning to a theme we touched on earlier, but exploring it in somewhat greater depth. What this particular object tells us about the diversity and the complexity of the pathways that stars can follow as they approach the ends of their respective lives. For much of the 20th century, the standard picture of stellar evolution, particularly for stars of roughly the Sun's mass or somewhat greater, involved a relatively orderly, relatively predictable sequence of stages. A long, stable period of hydrogen fusion in the core, followed by an expansion into a red giant as core hydrogen becomes exhausted, followed by helium fusion and further structural changes during the asymptotic giant branch phase, followed by a relatively gradual shedding of the outer envelope and culminating in the formation of a planetary nebula surrounding an exposed, slowly cooling white dwarf core. This basic outline remains broadly accurate and broadly useful as a general framework for understanding how stars of this mass range evolve. But the discovery of objects like the Boomerang Nebula, along with the broader, ongoing study of the diverse population of planetary nebulae and pre-planetary nebulae that astronomers have catalogued throughout the galaxy, has revealed that the specific details of this general process can vary dramatically from star to star, producing a remarkably diverse range of specific outcomes, different shapes, different mass loss rates, different timescales, and, as we have explored at length tonight, different resulting temperatures, all nested within the same broad, general evolutionary framework. This diversity has pushed astronomers to develop increasingly sophisticated theoretical models of stellar evolution, models that attempt to account not just for the broad general sequence of evolutionary stages that most stars of a given mass range will pass through, but also for the specific factors: binary companions, rotation rates, magnetic fields, subtle differences in chemical composition that can cause individual stars to deviate from the most typical, most average pathway in various specific and sometimes dramatic ways. The Boomerang Nebula, in this sense, has served as something of a touchstone object within this broader research program, a particularly well-studied, particularly extreme example that has helped motivate and inform the development of more sophisticated, more nuanced models of exactly how and why some dying stars produce such unusually dramatic, unusually rapid episodes of mass loss, while the majority of stars passing through this same general evolutionary phase do so in a comparatively gentler, comparatively more typical fashion. There is a related thread worth pulling on here concerning the broader question of how common objects like the Boomerang Nebula actually are throughout the galaxy, and what this tells us about the overall population statistics of dying stars more generally. Planetary nebulae and pre-planetary nebulae, as a general category, are relatively short-lived phenomena on astronomical timescales, typically persisting in their visible, recognizable form for perhaps only 10 to 20,000 years before the expanding gas disperses too thinly to remain easily detectable, and before the central star itself cools and fades to the point where it can no longer effectively illuminate or ionize whatever surrounding gas remains. This means that at any given moment, only a relatively small fraction of all the stars that will eventually pass through this evolutionary phase are actually visible to us as planetary nebulae, since most stars that have already passed through this brief, transitional phase have already faded from easy detectability, while many other stars that will eventually pass through this same phase have not yet reached that point in their evolution. Despite this inherent brevity, astronomers have nonetheless catalogued several thousand planetary nebulae throughout the Milky Way, along with a smaller but still significant number of pre-planetary nebulae, objects like the Boomerang Nebula, caught at the even earlier, even more transient stage before the central star has become hot enough to fully ionize its surrounding ejected gas. This catalogue, while almost certainly incomplete, Given the difficulty of detecting faint, distant, or heavily obscured examples of these objects, provides a valuable statistical sample for studying the overall diversity of outcomes that this particular evolutionary phase can produce. Within this broader catalogue, objects displaying the kind of extremely fast, extremely massive outflow that characterizes the Boomerang Nebula appear to represent a relatively small minority, suggesting that while the basic phenomenon is not entirely unique to this one specific object, it does represent a genuinely unusual and genuinely extreme outcome relative to the more typical, more moderate mass loss rates and outflow velocities observed in the broader population of similar objects throughout the galaxy. This statistical context is useful for properly calibrating our sense of just how remarkable the Boomerang Nebula actually is. It is not simply an arbitrary, isolated curiosity entirely disconnected from the broader population of similar objects throughout the galaxy. It is, instead, a genuine statistical outlier within a well-studied and reasonably well-characterized broader population, a particularly extreme example drawn from one tail of a distribution of outcomes that, while centered on more typical, more moderate behavior, clearly extends, in at least a small number of documented cases, toward the kind of dramatic, rapid, extreme mass loss that has earned the Boomerang Nebula its particular, well-deserved scientific fame. Let's pause for a moment and consider the broader emotional and aesthetic dimension of an object like the Boomerang Nebula, much as we considered the quiet beauty of the Boötes Void's emptiness in a previous episode, because there is something genuinely moving, in its own particular way, about the specific combination of violence and cold that this object represents. The Boomerang Nebula is, in a very real sense, the visible signature of a star's death throes, the dramatic final act of a stellar life that, for billions of years prior, proceeded along a comparatively calm, comparatively stable trajectory of steady hydrogen fusion. And yet, the specific character of this particular death, this unusually rapid, unusually violent shedding of mass, has produced, as an almost paradoxical byproduct, one of the coldest, most quiet, most physically subdued environments known anywhere in the universe. Violence and cold, dramatic upheaval and profound quiet exist here side by side, intimately connected, one giving rise directly to the other through the specific physics of adiabatic expansion that we have explored at length tonight. There is a kind of poetry in this connection that feels worth dwelling on for a moment. The most extreme cold we know of in the natural universe is not produced by some serene, undisturbed corner of deep space, quietly settling toward equilibrium over countless eons. It is produced, instead, by violence, by the dramatic, rapid, almost catastrophic shedding of a dying star's outer layers, the kinetic fury of gas rushing outward at well over 100 kilometers per second. The cold, in this case, is not the absence of activity. It is, paradoxically, the direct and immediate product of an unusually intense and unusually energetic process. Energy not being added to the system, but being actively, dramatically extracted from the random thermal motion of its constituent particles and redirected into the orderly, directional motion of the expansion itself. This pairing of violence and cold, of dramatic stellar death and the resulting almost serene extremity of low temperature, offers its own particular kind of lesson about the universe's capacity to produce genuinely surprising, genuinely counterintuitive outcomes from the careful, lawful operation of its underlying physical principles. We tend, in ordinary human experience, to associate violence and rapid, dramatic change with heat, with fire, with the release rather than the absorption of energy. The Boomerang Nebula offers a quiet but genuinely striking counterexample, a reminder that the relationship between energy, motion, and temperature is considerably more subtle and considerably more interesting than our everyday intuitions might initially suggest. As we continue moving toward the close of tonight's exploration, let's consider one more facet of the Boomerang Nebula's story, one that connects to a broader theme we have returned to repeatedly across our explorations together on this channel: the relationship between the scale of human observation and the scale of the phenomena being observed. The Boomerang Nebula sits roughly 5,000 light-years from Earth, a distance that, while modest compared to the truly vast scales we explored in our episodes about the Botha's Void or the broader cosmic web, is still almost unimaginably large by the standards of everyday human experience. A distance so great that the light reaching our telescopes tonight, carrying the information that allows us to study and to understand this remarkable object, actually left the nebula roughly 5,000 years ago, around the time of the earliest written human civilizations, long before any of the specific scientific concepts we have explored tonight: thermodynamics, quantum mechanics, the cosmic microwave background, had been developed or even conceived of by anyone. This means that the dramatic, violent mass loss episode we have been discussing tonight, the specific physical process responsible for producing the record-breaking cold that astronomers measured in 1995, was actually occurring in real cosmic time, roughly 5,000 years before that measurement was taken, give or take the additional time required for the light and radio signals we observe to make their long journey across the intervening distance. The nebula we observe today, in other words, is not necessarily identical to the nebula as it actually exists right now, in whatever sense simultaneity has meaning across such vast cosmic distances. It is, instead, a kind of historical snapshot, a record of conditions as they existed several thousand years in the past, carried to us across the vast intervening gulf of space by the patient, reliable but finite speed of light and radio waves. This temporal dimension, much like the temporal dimension we explored in detail when discussing the Botha's Void and the Great Attractor in previous episodes, adds an additional layer of richness and an additional layer of humility to our understanding of the Boomerang Nebula. We are not observing this remarkable phenomenon as it exists in some absolute universal present moment. We are observing a careful, detailed historical record of a phenomenon that occurred and that has continued evolving over the roughly 5,000 years since the light we currently observe first began its long journey toward Earth. The actual, current state of the Boomerang Nebula, whatever that might mean in the context of an object so distant and so dynamically evolving, almost certainly differs in various specific details from the state we have spent this evening so carefully exploring and describing. Let's draw together, for these final, extended moments of tonight's exploration, the various threads we have followed, weaving them into something resembling a complete and satisfying understanding of the object and the phenomenon we set out, at the very beginning of this evening, to explore. We began with a simple, almost paradoxical-sounding claim, that the universe contains a place colder than the universe's own ambient background temperature, a place that, by the ordinary expectations established through our understanding of the cosmic microwave background, simply shouldn't exist. We have spent the subsequent hours of this exploration carefully unpacking exactly how and why such a place can, in fact, exist without violating any fundamental law of physics through the specific, dramatic mechanism of adiabatic cooling associated with an unusually rapid and unusually massive stellar outflow. We have explored the underlying physics of temperature itself, the absolute flaw established by the third law of thermodynamics, and the specific way in which the Boomerang Nebula approaches, though does not reach, that ultimate theoretical limit. We have explored the specific astronomical history of how this remarkable object was discovered, the careful radio observations of carbon monoxide absorption against the backdrop of the cosmic microwave background that first revealed its extraordinary temperature in 1995. We have explored the broader stellar evolutionary context, the transition from red giant to asymptotic giant branch star to pre-planetary nebula to eventual planetary nebula, and the specific dramatic superwind phase that the Boomerang Nebula's central star appears to be passing through right now. Or rather, as we just discussed, roughly 5,000 years ago from the perspective of cosmic time. We have considered the broader scientific significance of this discovery, its connections to the study of stellar mass loss and planetary nebula shaping more broadly, its connections to the broader chemical enrichment of the galaxy that we explored in detail in a previous episode, and its place within the broader catalogue of cosmic extremes and cosmic superlatives that the universe, across its vast extent and its vast age, has produced. And we have considered, throughout, the deeper philosophical and aesthetic dimensions of this particular cosmic story, the relationship between violence and cold, between extremity and ordinariness, between the patient, careful work of scientific measurement and the genuine, lasting wonder that such measurement can reveal. There is one final thought worth holding gently as we prepare to let tonight's exploration settle fully into rest, and it concerns the relationship between this specific cosmic story and the broader sense of wonder that explorations like this one are ultimately meant to cultivate. The Boomerang Nebula is, in the end, a relatively small, relatively modest object by the standards of the truly vast cosmic structures we have explored in previous episodes. A single, dying star and its associated expanding shell of gas, spanning perhaps half a light year, a distance that, while vast by any everyday human standard, is genuinely tiny compared to the 100,000 light-year span of our entire galaxy, let alone the hundreds of millions of light-years spanned by the great cosmic voids or the great attractor's vast supercluster basin. And yet, despite this comparatively modest scale, the Boomerang Nebula has earned its place as a genuinely significant and genuinely fascinating object of scientific study, not because of its size, but because of the specific, remarkable physical extremity it represents. A temperature that pushes against the very boundaries of what physics permits, achieved not through some special, rare cosmic circumstance, but through the ordinary, lawful operation of stellar physics, playing out in an unusually dramatic and unusually compressed fashion. This reminds us, gently, that wonder in the universe does not require vastness alone. It requires, instead, a willingness to look carefully, to measure patiently, and to think rigorously about what specific, careful measurements actually reveal about the underlying physical reality they describe. The Boomerang Nebula, modest in size but remarkable in its specific physical properties, offers exactly this kind of focused, careful wonder, a reminder that the universe's capacity to surprise and to delight does not depend solely on scale, but on the careful, patient attention that reveals just how strange and just how remarkable even a single, relatively modest dying star can become, when examined with sufficient care and sufficient curiosity. The night has grown quiet now, and the image of that distant, impossibly cold nebula can settle finally into the gentle background of your awareness, where it belongs, not as a source of unease, but as one more small, precious piece of cosmic strangeness, carefully understood, gently held, ready to be carried into the rest that awaits. 5,000 light-years away, and 5,000 years in the past, a star continued its dramatic, rapid transformation, shedding its outer layers with a violence and a speed that, through the careful, lawful physics of expansion, produced a cold beyond what the rest of the universe's gentle, ancient background radiation should have permitted. That cold, briefly and dramatically extreme, has already begun in the time since that ancient light set out on its long journey toward us, the slow process of warming back toward the universal background, fading, gradually, from record-breaking extremity back toward cosmic ordinariness. And here, in this specific, warm, comfortable moment, wherever you happen to be resting tonight, none of that distant drama touches you directly. You remain warm, settled, safe, entirely untouched by the violence and the cold that, 5,000 light-years away, continue to play out according to the same patient, lawful physics that governs every corner of the universe, including this one, including you, including the simple, quiet comfort of wherever you happen to be resting right now. If tonight's careful exploration of the universe's coldest known natural place has given you something worth carrying into sleep, a quiet appreciation for just how strange, just how lawful, and just how genuinely wonderful the universe's careful operation of physics can become, you are always welcome back at Beyond the Cosmos, whenever curiosity calls you toward another patient, careful exploration of the cosmos and its many remarkable corners. For now, let the cold recede fully into the distance, fading as it always was destined to do, back toward the universe's gentle, ancient, ambient warmth. And let your own immediate, present warmth, here, now, be enough. Before we let the night take over entirely, there is one more dimension of this story worth exploring, one that brings together several of the threads we have followed tonight into a slightly different, and I think, genuinely illuminating configuration. The question of what the Boomerang Nebula can teach us about the limits of our own intuition when it comes to understanding the universe. Human intuition about temperature, like human intuition about so many other physical quantities, is built almost entirely from everyday experience, from the narrow range of conditions encountered in daily life here on the surface of a temperate planet, orbiting a stable, moderate star within a comfortable, breathable atmosphere. Within this narrow range, cold means something specific and familiar. The chill of a winter morning, the cold of an ice cube, the deep cold of a freezer. Our intuitive sense of how cold can become, how cold is even possible, is calibrated entirely against this narrow, familiar range of everyday experience. The Boomerang Nebula, and indeed the broader field of astrophysics more generally, regularly reveals just how poorly this everyday intuition scales to the genuinely extreme conditions found throughout the wider universe. A temperature of 1 Kelvin is not simply colder than anything in everyday experience by some moderate factor. It represents a temperature so far removed from anything encountered in daily life that the usual intuitive sense of what cold even means largely breaks down, replaced by the need for careful, quantitative, scientifically grounded understanding rather than simple extrapolation from familiar experience. This pattern, where careful scientific investigation reveals phenomena that lie far outside the bounds of ordinary intuition, recurs throughout nearly every domain of astrophysics and indeed throughout physics more broadly. The speeds involved in galactic rotation, the densities involved in neutron stars, the temperatures involved in stellar cores, the timescales involved in cosmic evolution, all of these regularly exceed, by enormous factors, anything that everyday human intuition would naturally anticipate or naturally find comprehensible without careful, deliberate effort. The Boomerang Nebula, in this sense, serves as a particularly vivid and particularly accessible entry point into this broader pattern, precisely because temperature is a quantity that everyone has direct, intuitive, everyday familiarity with, making the specific extremity involved a natural object colder than the universe's own ambient background radiation, especially striking and especially effective at illustrating just how dramatically the universe's actual behavior can exceed the boundaries of our everyday intuitive expectations. Let's also take some time to consider the relationship between the Boomerang Nebula and the broader public fascination with cosmic superlatives, records, and extremes. A fascination that this very channel, in its own way, regularly draws upon and seeks to explore with appropriate scientific care and appropriate intellectual honesty. There is something genuinely compelling, at a deeply human level, about the idea of records and extremes. The tallest mountain, the deepest ocean trench, the fastest animal, the coldest natural temperature anywhere in the universe. This fascination likely reflects something fundamental about how human curiosity operates, a tendency to be drawn toward boundaries, toward limits, toward the edges of what is possible, perhaps because understanding these boundaries helps us build a more complete and more accurate mental model of the full range of phenomena that the universe or our own planet is actually capable of producing. The Boomerang Nebula's status as the coldest known natural place in the universe taps directly into this fascination, offering a genuinely compelling, genuinely memorable hook for engaging with a much broader and much more technically intricate set of underlying scientific concepts. The physics of stellar evolution, the thermodynamics of gas expansion, the methods of molecular line astronomy, and the broader history of how astronomers have gradually built up an increasingly detailed and increasingly accurate picture of how stars live, age, and eventually die. This is, in fact, one of the genuine values of approaching scientific education and scientific communication through the lens of records and extremes. These particularly dramatic, particularly memorable examples can serve as effective entry points, drawing curious minds into a deeper engagement with the broader, more technical scientific concepts that explain why and how these particular extremes come to exist. Few people, encountering the Boomerang Nebula for the first time, are initially drawn in by an abstract interest in adiabatic cooling or stellar mass loss rates. They are drawn in, instead, by the simple, striking, almost paradoxical-sounding claim that the universe contains a place colder than the universe's own ambient temperature, a claim that, once encountered, naturally invites the kind of deeper, more careful exploration that we have spent this entire evening pursuing together. There is a final, somewhat more speculative thread worth pulling on before we close tonight's exploration. One that touches on the question of whether objects like the Boomerang Nebula might have any broader relevance to questions of astrobiology and the search for life elsewhere in the universe, themes we explored at considerable length in our previous episode about the universe's many dead zones. At first glance, an object like the Boomerang Nebula might seem to have little direct relevance to questions of habitability, since the extreme, violent conditions present within and immediately surrounding a dying star's rapidly expanding outer envelope would almost certainly be incompatible with any plausible form of life, at least during the specific dramatic phase of stellar evolution we have spent this evening exploring. Any planets that might have orbited this particular star earlier in its life, during its long, stable, hydrogen-fusing phase, would very likely have been engulfed, or at least dramatically and catastrophically disrupted by the star's subsequent expansion into a red giant and its later, even more dramatic shedding of mass during the superwind phase responsible for the Boomerang Nebula's extreme cold. However, as we discussed in our previous episode on cosmic dead zones, the chemical enrichment that results from this kind of dramatic stellar mass loss, the heavy elements forged within the star's interior over its multi-billion-year lifetime, scattered outward into the surrounding interstellar medium, eventually becomes incorporated into the next generation of stars and planets that will form from that enriched material in the future. In this sense, even the most violent, most apparently inhospitable phases of stellar evolution, the dramatic rapid mass loss exemplified by the Boomerang Nebula, contribute directly and meaningfully to the long, slow, multi-generational process of galactic chemical enrichment that, given enough time and enough successive stellar generations, eventually makes planets like Earth and life like our own possible. This offers a particular kind of closing perspective worth holding on to, that even the most extreme, most dramatic, and most apparently destructive phases of cosmic evolution, the violent death throes of a star, the record-breaking cold produced by that star's rapid disintegration, ultimately serve a constructive, generative purpose within the much longer arc of cosmic and chemical history. The same dramatic, violent process responsible for producing the coldest known natural place in the observable universe is also, simultaneously, contributing the very heavy elements that will, eventually, somewhere in the galaxy, at some point in the future, become part of new stars, new planets, and perhaps, given sufficient additional time and sufficient additional favorable circumstances, new life. As we move to genuinely close tonight's exploration, let's allow ourselves one final quiet moment of synthesis, drawing together the scientific, the philosophical, and the simply wonder-filled threads that we have followed across this long evening. The universe, vast and ancient and governed throughout its entire extent by a comparatively small, comparatively comprehensible set of fundamental physical laws, has produced, in one small, particular corner of itself, a result that initially seems to defy the most basic expectations we carry about how cold the natural world can become. And yet, upon careful, patient examination, this apparent paradox resolves cleanly and completely into a beautiful, lawful demonstration of exactly how powerful those same fundamental physical laws can become when applied to sufficiently extreme circumstances. An entire star's outer envelope rushing outward into the vacuum of space at speeds and at rates far beyond anything encountered in more typical, more gentle stellar evolution. This pattern, extraordinary outcomes emerging lawfully and comprehensibly from ordinary physical principles applied at extraordinary scales, is perhaps the single most important and most recurring lesson that careful, patient astronomical investigation has to offer. A lesson we have now encountered repeatedly across our explorations together on this channel, from the largest known cosmic void to the most massive nearby concentration of gravitating matter to, tonight, the coldest known natural place anywhere in the observable universe. And throughout all of this, the universe continues operating exactly as it always has, indifferent to whether any conscious observer happens to notice or to understand the particular extremities it produces, indifferent to the careful, patient measurements that astronomers undertake to reveal and to explain those extremities, indifferent even to the quiet, late-night curiosity that has brought you here tonight, to sit with these ideas as you drift toward your own rest. And yet, despite that fundamental indifference, the universe has, through the patient, careful work of human scientific investigation, become a little more known, a little more understood, a little more available to genuine human wonder and genuine human appreciation. One careful measurement, one patient explanation, one quiet evening of reflection at a time. The Boomerang Nebula will continue its dramatic, rapid expansion long after tonight's exploration has ended, long after you have drifted into sleep, long after this particular evening has become, itself, a small, settled piece of your own personal history. 5,000 light-years away, the dying star at its heart will continue shedding its outer layers. The expelled gas will continue its outward rush into the vacuum, gradually cooling, gradually warming back toward the universal background, gradually, over the coming centuries, fading from cosmic extremity back toward cosmic ordinariness. None of that ongoing, patient, lawful process requires your attention or your awareness to continue unfolding exactly as it always was going to unfold. And yet, in choosing to spend this evening exploring it carefully together, you have done something worth honoring. You have allowed a small, distant, otherwise unremarkable seeming patch of glowing gas in the constellation Centaurus to become, for this one evening, a genuine source of wonder, a genuine occasion for careful thought, a genuine reminder of just how strange, just how lawful, and just how worth understanding the universe's quiet, patient operations actually are. That is, in the end, perhaps the deepest and most lasting gift that careful astronomical exploration has to offer. Not simply a collection of facts about distant objects, however genuinely fascinating those facts might be, but a renewed, deepened sense of the universe's own quiet, patient, lawful strangeness, available to be discovered, examined, and appreciated by anyone willing to look carefully enough, to measure patiently enough, and to think rigorously enough about what those careful measurements actually reveal. If tonight's exploration of the universe's coldest known place has given you something worth carrying gently into rest, you are always welcome back at Beyond the Cosmos, whenever curiosity calls you toward another of the universe's quiet, patient, remarkable corners. There is always more to discover, always another careful measurement waiting to reveal some new facet of how the cosmos actually operates, and always, here, a calm and curious space to explore those discoveries together. For now, let the distant cold fade fully into the quiet background of the night, and let your own gentle warmth here, in this moment, be enough. One last thought before the silence settles in fully. Throughout tonight's journey, we kept returning to a single quiet observation: that the universe's most extreme outcomes are rarely the product of exotic, unfamiliar physics, but are instead the familiar laws of nature, pushed to their furthest natural limits by circumstance and scale. A can of compressed air cooling your hand, scaled up to the mass of a star and the speed of an explosion, becomes a record that the whole observable universe has, so far, failed to surpass. There is a kind of reassurance buried in that pattern, one worth carrying forward past tonight and into whatever else this channel explores together with you in the future. The universe does not require a separate rulebook for its strangest, most extraordinary corners. It requires only patience, scale, and the willingness of careful observers here on a quiet, temperate planet orbiting an unremarkable star to measure carefully enough to notice when those ordinary rules have been pushed somewhere truly remarkable. 5,000 light-years away, in the gentle afterglow of a dying star's final dramatic act, the coldest known place in the universe continues its slow, patient fade back toward the ordinary. And here, now, in the quiet of wherever you are resting, the warmth around you is enough, has always been enough, and will remain enough, long after the last echo of tonight's exploration has faded into sleep. And so, as this long, slow evening finally draws to its true close, the image we carry forward is a simple one. A faint, boomerang-shaped glow in a southern constellation, ordinary to the eye, extraordinary to careful instruments, holding within its gently expanding gas a temperature that the universe's own ambient warmth should never have permitted. A reminder that even in a cosmos built from familiar, comprehensible laws, there is always room for genuine surprise, waiting patiently to be found by anyone willing to look closely enough and to measure carefully enough to notice it. Rest now. The cold is far away and fading further with every passing year. The warmth here is yours. Good night.